You've probably used an AI like ChatGPT, right? But have you ever stopped to wonder how it actually gets built? How does it go from, a bunch of code to something that can write a poem or explain quantum physics? Well, it's not magic. It's more like an epic two-act play full of massive data sets, incredible computation, and some seriously clever engineering. So let's pull back the curtain and see how these tools really come to life.
So here's the game plan. We'll start with the big picture idea that really changed how AI is made. Then we'll dive into Act 1, which is this insane brute force learning phase. We'll look at the mind-boggling engineering it takes to even pull that off. After that, it's on to Act 2, where we take that raw knowledge and turn it into something genuinely useful. We'll cover the clever tricks that make it efficient, and then we'll wrap up by asking the hardest question of all. How do we even know if the final result is any good?
All right, first things first. To really get how we build AI today, you've got to understand that the whole strategy has flipped. We used to build a bunch of little specialists, now we build one superpowered generalist.
Yeah, back in the day, if you wanted an AI to catch spam emails, you had to build a spam detector from the ground up. Then, if you needed another AI to analyze customer reviews, guess what? You'd build a totally separate model, again, from scratch. It was a huge waste of time and resources. The new way of thinking, what we call transfer learning, is so much smarter. You do the really heavy lifting just one time. You pre-train one gigantic foundational model that just understands language. Then you can make little tweaks to that one model to adapt it for all sorts of different jobs. And that brings us to Act 1, the pre-training gauntlet. Seriously, this is the most expensive, the most time-consuming, and the most computationally massive part of the whole shebang. This is where the model just learns the raw, fundamental patterns of human language and knowledge. So the actual task here sounds almost ridiculously simple. Just predict the next word. You feed the model trillions of words, and for every single one, its only job is to guess what's coming next. But by forcing it to do this over and over and over, it has to learn everything. Grammar, facts, different styles of reasoning, even the subtle clues in a conversation. It's a simple goal with incredibly complex results. And when we say vast amounts of data, we are not kidding. The model's diet is basically everything. It scrapes a huge portion of the public internet. It reads all of Wikipedia to learn facts, tons of books to understand storytelling, Reddit to see how people actually talk, and even GitHub and Stack Overflow to learn the languages of computer code. It's basically learning from the entire digital shadow of humanity. To put this in perspective, let's look at GPT-3. This was the model that felt like science fiction just a few years back. It was trained on an absolutely staggering 300 billion tokens. And a token is basically a word or a piece of a word. That's a library of text that's almost impossible for a human to comprehend.
But here's where things get really wild. The race for more data is relentless. A newer model, Llama 3, wasn't trained on a little more. It was trained on 15 trillion tokens. Let that sink in for a second. That is a 50 times increase. It's not just a step up, it's a leap to a whole different planet. The core belief in this field has been that more data equals a smarter AI, and this number just shows that philosophy in action.
So, okay, you've got 15 trillion tokens of data and a model with hundreds of billions of internal knobs or parameters that it needs to tune. This creates an engineering problem of epic proportions. This is where the real heroes of hardware and software have to step in and figure out how to make the impossible possible. And here's the fundamental problem. The model itself, the data it's crunching, and all the math it has to do along the way, it just plain doesn't fit in the memory of a single computer. Not even the most powerful, tricked-out GPU in the world can handle it. So, what do you do? At its heart, the training process is just a simple loop that runs trillions of times. First, in the forward pass, data goes through the model and it makes a guess. Then, in the backward pass, it looks at its guess, compares it to the right answer, and calculates how wrong it was. Finally, in the weight update, it adjusts itself just a tiny bit to be less wrong the next time. The problem is, to do that backward pass and the update, it has to remember every single calculation it made on the way forward. And all that bookkeeping just eats up a ton of memory. The answer, as you might guess, is parallelism. If you can't use one giant computer, you use an army of smaller ones working in perfect sync. You can split the data up, giving each GPU a different chunk to work on. Or, if the model itself is the problem, you can literally slice the model into pieces and have each GPU hold a different part of the AI's brain. And then there are super clever techniques like Zero, which just makes sure that no two GPUs are wasting memory by holding on to the same piece of information. And this leads to one of the biggest software breakthroughs, something called flash attention. Okay, think of a GPU's memory like a kitchen. It has a giant, slow walk-in pantry in the back. That's its main memory. And it has a tiny, super fast spice rack right next to the stove. That's its on-chip memory. The old way of doing things involved running back and forth to the slow pantry for every single ingredient. Flash Attention is a genius recipe that reorganizes the math so it can do almost all the work using just the stuff on that super fast spice rack, which minimizes those slow trips and makes everything way, way faster.
And that brings us to Act 2. So we have our pre-trained model. It's this massive brain that has essentially read the entire internet. It knows a lot, but it's not actually helpful yet. It's like a brilliant librarian who, when you ask a question, just starts shouting random encyclopedia entries at you. Now we need to teach it some manners and how to have a normal conversation.
So check this out. Before fine-tuning, if you ask the raw model a simple question like, "Can I put my teddy bear in the washer?" it doesn't really answer you. It just continues the sentence based on patterns it's seen. It knows what a teddy bear is made of, sure, but it totally misses your intent. It's spitting out facts, not a helpful answer.
Now look at the difference after fine-tuning. Same prompt, totally different world. The model understands the question behind the question, it considers the context, it thinks about safety, and it gives you a genuinely helpful recommendation. It's gone from being a text predictor to an actual assistant. And that transformation, that's the entire point of Act 2.
This process is called supervised fine-tuning, or SFT for short. What we do is we take our giant pre-trained model, and now we feed it a much smaller, carefully curated dataset. This isn't just random text from the internet. It's thousands of high-quality examples of prompts and the perfect, helpful, safe responses to go with them. This is basically where the model goes to finishing school, to learn how to follow instructions and act like a human would want it to.
But hold on, fine-tuning a model with hundreds of billions of parameters still sounds incredibly expensive, right? And it would be, except this need has sparked its own revolution in efficiency, creating new techniques that make customizing these powerful AIs accessible to way more people.
The absolute star of this revolution is a technique called LoRa, and the core idea is just genius. Instead of retraining the whole massive model, you freeze it. You don't change a single one of its original parameters. Instead, you train a very small, separate set of new weights, like tiny little adapter modules, that get plugged into the model. Think of it this way. You're not trying to rewrite an entire textbook, you're just adding a few very smart sticky notes. It's incredibly efficient. And this chart just says it all. If fully fine-tuning a model means you have to update 100% of its parameters, LoRa often lets you get the same result by updating less than 1%. I mean, that is a monumental drop in the amount of computing power you need. It's a total game changer. And just when you think it can't get any better, it does. There's an even more efficient version called QLoRa. It takes that same LoRa sticky note idea and adds another trick called quantization. All that means is that it stores the numbers in the big, frozen part of the model with less precision, kind of like rounding them off to save space. The result? You can now fine-tune absolutely enormous, state-of-the-art models on a single gaming computer. This is what's truly democratizing AI. So we did it. We've built our model. We pre-trained it on the internet. We fine-tuned it to be helpful. Now for the final act. We have to give it a grade. And this is where things get surprisingly tricky and, frankly, a little subjective. How do you actually measure if an AI is good? Generally speaking, there are two main ways we do this. On one hand, you have academic benchmarks. These are basically standardized tests for the AI, like the SATs, that grade it on things like math, law, and common sense reasoning. On the other hand, you have human preference, where real people are shown two different AI answers to a question, and they just vote for which one they think is better. But here's the catch. Both of these methods are flawed. Those benchmarks can be gamed if the model has already seen the test questions or something very similar in its training data. And with human voters, well, we're not always experts. Plus, our preferences are totally subjective. Some people love when an AI uses emojis. Others hate it. And what's really fascinating is that human voters will often penalize a model for being too safe, for correctly refusing to answer a dangerous or harmful question. All of this leaves us with a really fundamental, deep question that's less about engineering and more about philosophy. If a model can ace every single exam we throw at it, but we can't fundamentally trust it to be safe or aligned with our values, then what have we really built? And what does intelligence even mean in that world?